Go outside tonight. If you can, go somewhere dark, away from the streetlights, away from the orange glow of the city that has stolen most of the night sky from most of us. Find a field, a hillside, a dark road in the country. Let your eyes adjust for 10 or 15 minutes until the darkness becomes something rich and detailed rather than simply absent. Look north. Find the W shape of Cassiopeia, those 5 bright stars arranged like a lazy letter W scratched across the sky. And then look just slightly below and to the left of that W, into the dimness between the stars. If the night is truly dark, and if you know exactly where to look, you will see something. Not a star. A star is a point of light, sharp and defined. This is something else, a soft smudge, barely there, like a thumbprint pressed in light, a faint oval haze that seems to dissolve if you look at it directly and reappear when you look slightly away. That smudge, that barely there whisper of light, is one of the most extraordinary things in the sky. It is a galaxy. Not our galaxy. Not the Milky Way, whose edge we are standing inside, whose band of light arches overhead on a clear night. This is another galaxy entirely. A separate island of stars, separated from us by a distance so large that the number of kilometers involved is almost meaningless, a distance so vast that the only honest way to describe it is to say. The light you are seeing right now left that galaxy 2.5 million years ago. When that light began its journey toward your eye, our human ancestors were still learning to chip stone into tools on the African savanna. The entire span of recorded human history, every war, every empire, every invention, every great work of art and science and literature, fits into the last instant of that light's journey. The smudge of light is called the Andromeda galaxy. It is the most distant object visible to the naked human eye. It is our nearest large galactic neighbor. It is falling toward us. And it contains, by most estimates, roughly 1 trillion stars. 1 trillion stars, and you can see it with your bare eyes, on a dark enough night, as a faint smudge in the northern sky. Welcome, Midnight Explorer. Tonight, we are going to Andromeda. Not physically, we can't. Even at the speed of light, the journey takes 2.5 million years. But we are going to go there in every other way available to us. Through history, through the long, astonishing story of how human beings came to know what this smudge of light is. Through science, through the remarkable facts of what Andromeda actually is, what it is made of, what is happening inside it. Through time, into the future, where Andromeda and our galaxy are moving toward each other on a collision course that will play out over billions of years. And through the deepest question this galaxy raises when you really look at it, what does it mean to stand here, on this small planet, and see something that far away, and know what it is? The Andromeda galaxy has been in our sky for as long as our species has existed. And for almost all of that time, we had no idea what we were looking at. This is the story of how we found out. The year is 964 CE. The place is somewhere in Persia. Possibly in Isfahan, possibly in the city of Shiraz, or perhaps in the great observatory culture that had developed across the Islamic world in the centuries following Muhammad. A Persian astronomer named Abd al-Rahman al-Sufi is completing one of the great works of medieval astronomy, his Book of Fixed Stars, Kitab Suwar al-Kawakib al-Thabita. A meticulous catalogue of the positions and brightnesses of the stars visible from his latitude, updating and correcting the ancient Greek catalogue of Ptolemy with his own careful observations. Al-Sufi is systematic, patient, thorough. He observes each region of the sky, night after night, in the sharp desert darkness of the Persian plateau. He draws each constellation with care, noting the stars, their colors, their magnitudes. And when he comes to the constellation Andromeda, the princess of Greek mythology, daughter of Cassiopeia, chained to her rock above the sea, he records something unusual. He notes the existence of a sahabat, a cloud. A little cloud, he calls it, in the area of the constellation. He notes that it is visible to the naked eye, that it moves with the constellation across the sky, that it is not a star but something more diffuse. He includes it in his catalogue. He illustrates it in his drawings. That little cloud is the Andromeda galaxy. Al-Sufi is the first person in recorded history to observe the Andromeda galaxy and write about it. He had no way of knowing what it was, no framework for understanding a galaxy, no concept of a universe containing anything beyond our own. To him, it was a little cloud moving among the stars, a curiosity in the sky of Andromeda. But he saw it. He recorded it. He passed the knowledge forward. His Book of Fixed Stars was translated into Latin and became one of the foundational texts of medieval and Renaissance astronomy. His name survives in the star Azophi, named in his honor. And his observation of the Andromeda, little cloud, appears in the astronomical literature of the following centuries, a data point that persisted until someone finally knew what to do with it. Before Al-Sufi, the Andromeda galaxy had surely been seen by countless human beings across countless millennia. The indigenous Australians, who developed the most sophisticated naked-eye astronomy of any culture, likely had observations and stories for it. The ancient Greeks may have seen it. Some researchers have suggested that the description of the Milky Way in ancient texts includes references to what might be the Andromeda patch of light. The peoples of the Arabian Peninsula and North Africa, in whose clear skies the galaxy is visible through much of the year, may have incorporated it into their star lore. But Al-Sufi is the first to write it down in a way that has survived. He saw the smudge in the sky above Persia, 1,000 years ago, in a world where the Earth was the center of the universe, where stars were light set in a crystalline sphere, where no one could have imagined that the little cloud was not in our sky but 2.5 million light-years away. He saw it. He recorded it. That is enough. The galaxy was seen. For the 7 centuries between Al-Sufi and Galileo, the Andromeda cloud appeared in various catalogues and star atlases. Simon Marius, a German astronomer, is credited with the first telescopic observation of it in 1612, a year after Galileo had demonstrated that the telescope could reveal new things in the heavens. Marius trained his small telescope on the Andromeda patch and wrote that it looked like a candle flame seen through a horn lantern, diffuse, soft, spreading outward from a bright center. The telescope did not resolve it into individual stars. It remained a cloud. A mystery with better edges, but still a mystery. Charles Messier, the 18th-century French astronomer famous for his catalogue of nebulae and star clusters, objects that might be mistaken for comets, which Messier was professionally engaged in hunting, included the Andromeda object as Messier 31, or M31. His catalogue entry, from 1764, describes it as a nebula without stars, resembling 2 converging cones of light. The catalogue entry persists. M31 is still Andromeda's catalogue name among astronomers, used alongside its more common designation. William Herschel, the German-born British astronomer who discovered Uranus in 1781 and who built the largest telescopes of his era, observed Andromeda extensively. His great reflector, with its 20-foot focal length and a mirror 1.5 feet in diameter, was the most powerful telescope in the world. He made careful observations of Andromeda's structure, noting what appeared to be dark patches near its center, speculating on its nature. Herschel believed that Andromeda and objects like it might be island universes, vast systems of stars at enormous distances, comparable in scale to our own galaxy. This was a radical idea. Most of his contemporaries assumed the nebulae were relatively nearby clouds of luminous gas within our own galaxy. The debate about what the nebulae were. Diffuse gas clouds, or distant star systems comparable to our own Milky Way, would continue for more than a century. It was called the Great Debate. And the answer, when it finally came, was more astonishing than either side had imagined. But let's not rush to the answer. The question is worth dwelling in. Because the Great Debate was not just an astronomical controversy. It was a confrontation with one of the deepest questions about the nature of the universe: how large is it? Are we alone in our stellar system, or is the Milky Way one of many? Is the universe everything we can see, or is there more, much more, impossibly more, beyond the edge of what our telescopes can reach? These questions mattered in a way that went beyond astronomy. If the Milky Way is the universe, if all those stars and nebulae and clusters are contained within a single great system, then we occupy a knowable whole. The universe is large, but comprehensible. Bounded, if incomprehensibly vast. But if the nebulae are distant galaxies, comparable to our own, if the Milky Way is one of many, and the universe contains not billions of stars but billions of stars arranged in billions of separate systems scattered across space that has no visible edge, then we are dealing with a universe of a fundamentally different character. Not just larger, but qualitatively different. More humbling. More vertiginous. More magnificent. April 26, 1920. The National Academy of Sciences, Washington, D.C. Two of the most prominent astronomers in America stood at opposite sides of one of the most consequential debates in the history of science. Harlow Shapley argued that the Milky Way was enormous, much larger than previously believed, and that the spiral nebulae, including Andromeda, were within or closely associated with it. They were, in his view, protosolar systems or other gas clouds, not distant star systems. Heber Curtis argued the opposite, that the spiral nebulae were island universes, distant galaxies comparable to the Milky Way, separated from us by vast distances. The debate was detailed, technical, and ultimately inconclusive on the night. Both men made good points. Both men made errors. The observational data available in 1920 was insufficient to definitively resolve the question. But the data was accumulating. And crucially, before the Great Debate, before the night in Washington, a revolution in how distance could be measured in the cosmos had already been accomplished, by a woman who had died of typhoid at 53, who worked under a supervisor who signed her papers as his own, whose name was not widely known outside her immediate scientific community. Her name was Henrietta Swan Leavitt. Henrietta Leavitt worked at the Harvard College Observatory as a computer. One of the women hired by observatory director Edward Pickering to analyze the enormous photographic plates the observatory was accumulating. These women, known, not entirely kindly, as Pickering's harem, did detailed, meticulous, exhausting work, cataloging stars, measuring their brightnesses, noting their positions. The work was considered sufficiently mechanical that women were hired for it at lower wages than men. It was not considered research. It was computation. But Leavitt was not just computing. She was thinking. Her particular assignment was to catalog the variable stars, stars whose brightness changes over time, in the Magellanic Clouds, the two small satellite galaxies of the Milky Way visible from the southern hemisphere. She worked through thousands of photographic plates, identifying and cataloging variable stars. And she noticed something. Among a type of variable star called Cepheid variables. Stars that pulsate rhythmically, growing brighter and dimmer over periods of days to weeks, there was a pattern. The brighter the Cepheid's average luminosity, the longer its pulsation period. A Cepheid that brightened and dimmed over 20 days was intrinsically more luminous than one that pulsated over 5 days. She published this observation, cautiously, in 1908. Then, in 1912, she published a refined version with 25 Cepheids, showing a clear, precise, linear relationship. The implication was enormous, though Leavitt stated it with characteristic understatement. If the period luminosity relationship was universal, if all Cepheid variables followed this same rule, then measuring a Cepheid's period gave you its true luminosity. And if you knew its true luminosity, and you could measure how bright it appeared in the sky, you could calculate how far away it was. A Cepheid variable was a cosmic measuring stick. A standard candle that could be used to measure distances to any object that contained one. Leavitt had given astronomers a ruler for the universe. She never got to use it in the way that would make her discovery famous. She died in 1921, the year before Edwin Hubble used her method to finally, definitively resolve the Great Debate. There is a painful footnote. A member of the Nobel Prize Committee tried to nominate Leavitt for the Nobel Prize in Physics in 1924. He wrote to Harvard Observatory to get her current address. The observatory replied that she had died 3 years earlier. The Nobel Prize cannot be awarded posthumously. Her discovery changed our understanding of the entire universe. Her reward was a footnote in someone else's story. We should say her name clearly. Henrietta Swan Leavitt. She measured the universe. Edwin Hubble was, by most accounts, not a modest man. He affected a British accent, though he was from Missouri. He wore a cape. He claimed to have been a lawyer before turning to astronomy, which was either an exaggeration or an outright fabrication. He was ambitious, self-promoting, and competitive. He was also, unambiguously, one of the greatest observational astronomers in history. In 1923, Hubble was working at Mount Wilson Observatory in California, using the Hooker telescope, the 100-inch reflecting telescope that was, at the time, the most powerful telescope in the world. He was examining photographic plates of the Andromeda Nebula. On October 4, 1923, he found what he was looking for. On a photographic plate of Andromeda's outer regions, he identified a variable star, a star that changed brightness over time in a characteristic pattern. He initially marked it with a N for nova, a new star. But as he examined more plates, as he traced the star's behavior over time, he realized it was not a nova at all. It was a Cepheid. He used Leavitt's period luminosity relationship. He measured the Cepheid's pulsation period. He calculated its true luminosity. He compared it to its observed brightness. The distance was staggering. Hubble's calculation put the Andromeda Cepheid, and therefore the entire Andromeda Nebula, at roughly 900,000 light-years away. The modern value, with much more refined measurements, is 2.537 million light-years. Hubble's calculation was off by a factor of about 2.5, because the calibration of the Cepheid period luminosity relationship itself would be refined in later decades. But even his underestimate was sufficient to prove the point. Andromeda was far outside our galaxy. It was not a nebula within the Milky Way. It was not a cloud of gas. It was not a protosolar system. It was a galaxy. Another entire galaxy, separate from ours, containing its own billions of stars, at a distance that made our own galaxy look small. Hubble reportedly wrote var. For variable, on the photographic plate in red pencil, over the N he had originally written. That photographic plate, with the red VR, scrawled on it in Hubble's hand, survives. It is perhaps the most consequential astronomical image in history, the moment when the universe grew by a factor we struggle to express in words. He wrote a letter to Shapley, the Great Debates' small universe proponent, informing him of the discovery. Shapley's response, on reading the letter, was reported to be, "Here is the letter that has destroyed my universe." He was right. The universe that Hubble's Cepheid measurement revealed was not merely larger than the one Shapley had defended in 1920. It was a different kind of universe. One in which the Milky Way was not the entirety of creation but one galaxy among what would eventually be understood to be hundreds of billions of galaxies, each containing hundreds of billions of stars. The night sky, which had seemed vast but ultimately bounded, turned out to be a window onto something for which we have no adequate word. Vast is inadequate. Incomprehensible is closer. And the smudge in the northern sky, the little cloud that Al-Sufi had noted 1,000 years earlier, was the key that opened the window. Let's stop the history for a moment and simply look at Andromeda. What is it? Andromeda, Messier 31, NGC 224, is a spiral galaxy. The type of galaxy most familiar to us from images in textbooks and science documentaries, a central bulge of closely packed, older stars, surrounded by a flattened disk in which younger stars and gas and dust are arranged in curving spiral arms that trail out from the center like the pattern of cream slowly stirred into coffee. It is large. Very large. The largest galaxy in our local group. The cluster of galaxies that includes the Milky Way, Andromeda, and approximately 50 smaller galaxies. Modern measurements put Andromeda's diameter at somewhere between 200,000 and 250,000 light-years across. For comparison, the Milky Way is estimated to be between 100,000 and 180,000 light-years in diameter. Andromeda is roughly twice the diameter of our own galaxy. Possibly larger. It contains, by most estimates, approximately 1 trillion stars. 1,000 billion stars. The Milky Way, by comparison, contains an estimated 200 to 400 billion stars. Andromeda dwarfs us in stellar population. Seen from above, as we see many galaxies in the famous Hubble images, Andromeda would appear as a gorgeous spiral, its arms wound around a bright central hub, glowing with the combined light of a trillion suns. But we don't see Andromeda from above. We see it from the side, or nearly so. The galaxy is tilted at approximately 77 degrees relative to our line of sight. From our perspective, we see the disk nearly edge-on, which is why it appears as an elongated oval smudge rather than the face-on spiral we might hope for. The central bulge, the galactic core, contains an enormous concentration of older, redder stars. There, at the very center, is something we will return to. A supermassive black hole with a mass approximately 100 million times that of our Sun. Our own Milky Way's central black hole, Sagittarius A*, has a mass of about 4 million solar masses. Andromeda's central black hole is roughly 25 times more massive. Surrounding the main disk is a vast halo of dark matter, invisible material that contributes to the galaxy's gravitational mass without emitting light. The halo extends far beyond the visible disk, merging at its outer edge with the halos of other nearby galaxies. And in orbit around Andromeda are its satellite galaxies, a retinue of smaller galaxies bound to it by gravity. The two most prominent, visible to the naked eye under very dark skies, are M32 and M110, compact elliptical galaxies that are the remnants of past galactic mergers. Andromeda has absorbed dozens of smaller galaxies over its history, and the current satellites are simply the most recent additions to an ongoing process of galactic cannibalism. Andromeda also has two satellite galaxies, NGC 185 and NGC 147, that are too faint for naked eye observation but visible through binoculars and small telescopes. And recent deep surveys have revealed dozens of dwarf satellite galaxies in Andromeda's halo, tiny companions orbiting the great galaxy in the darkness. The light that reaches your eye when you look at Andromeda on a dark night, that faint oval smudge, is the combined light of approximately 1 trillion stars, each shining across a gulf of 2.537 million light-years. To hold that fact in your mind, really hold it, not just intellectually acknowledge it, requires a kind of mental stretching that is at once uncomfortable and exhilarating. Your eye is catching the photons from a trillion stars. Each photon left its source star 537 million years ago. And traveled through intergalactic space, empty space, nearly absolutely empty, with occasional stray hydrogen atoms but essentially nothing, for 2.537 million years. And arrived at your eye. At this moment. At this specific night, and this specific gaze, on this specific hillside or dark field or rooftop. You are the end point of a 2.537 million year journey of light. Let's take a tour. Starting from outside and moving in. The outer halo. Modern surveys have revealed that Andromeda's halo of stars and dark matter extends far beyond the visible disk, potentially as far as 2 million light-years from the galactic center. This means Andromeda's halo nearly reaches the Milky Way. The two galaxies' halos may already be overlapping. Within the halo are the stellar streams, long, thin arcs of stars that trace the paths of smaller galaxies that Andromeda has shredded and absorbed. The giant stellar stream, discovered in 2001, is one of the most prominent, a tidal stream of stars stretching hundreds of thousands of light-years across Andromeda's halo, the remnant of a dwarf galaxy that fell into Andromeda perhaps a few billion years ago, was torn apart by tidal forces, and is now slowly spreading into the larger galaxy's halo. These stellar streams are like the footprints of past mergers. Evidence of the violence of galactic history, preserved in the positions of individual stars. Moving inward, the disk. The disk of Andromeda contains the familiar ingredients of a spiral galaxy. Gas, mostly hydrogen, both neutral hydrogen, HI, detectable at radio wavelengths, and ionized hydrogen in the regions around young, hot stars. Dust, complex organic molecules and silicate grains that block starlight and appear as dark lanes when silhouetted against the galaxy's glow. Stars of all ages, ancient red giants in the disk's outer regions, middle-aged stars like our Sun in the intermediate regions, and young blue-white stars blazing at the inner edges of the spiral arms, recently formed from the gas and dust of the disk. Star-forming regions, clouds of gas and dust so dense that they collapse under their own gravity, fragmenting into protostars, then into the stars of the next generation. Andromeda has many star-forming regions, visible in infrared images as knots of warmth in the cool dust lanes. The spiral arms, though in Andromeda, as seen nearly edge-on, the spiral structure is harder to trace than in a face-on galaxy. Multi-wavelength observations, combining visible light, infrared, ultraviolet, and radio data, reveal the arm structure more clearly than visible light alone. The ring structures. This is something not expected, and still not fully understood. Andromeda contains one or more ring-like structures in its disk, rings of star formation that are distinct from the classic spiral arm pattern. The most prominent is a ring of dust and star formation at roughly 32,000 light-years from the galactic center. Another ring exists at about 26,000 light-years. The current best hypothesis for these rings is that they were created by a collision. Not with another large galaxy, but with one of Andromeda's satellite galaxies, possibly M32, which may have plunged through Andromeda's disk in the past, leaving a ring of disturbed gas and triggered star formation in its wake. If this is correct, then the ring structures in Andromeda are the scars of a past impact, the galaxy wearing its history in its structure, the way a body carries the marks of old injuries. And at the center, the galactic bulge. The central region of Andromeda is dominated by old stars, stars that formed long ago, in the galaxy's youth, when the rate of star formation was much higher. These stars are redder and dimmer than the young blue giants of the spiral arms. They are the forest elders of the galaxy, if you like, ancient, central, and carrying the history of the galaxy's earliest chapters. And at the very center of the bulge, the nucleus. Andromeda's nucleus is double. Not a single central concentration of stars, but two distinct peaks of stellar density very close together. This double nucleus, discovered in the 1990s by the Hubble Space Telescope, is highly unusual and has provoked significant theoretical work. The current best explanation is that the brighter of the two nucleus components is an eccentric disk of stars orbiting the central black hole in very elongated orbits, spending most of their time near the orbit's far point, apoapsis. And thus appearing concentrated there. The dimmer component is the true center, containing the central black hole. The double nucleus of Andromeda is the visual signature of the dynamical influence of a 100 million solar mass black hole on the stars nearest to it. The black hole itself, of course, is invisible. Black holes emit no light. But its presence is written in the motions of the stars around it, stars moving at velocities that only a mass of 100 million suns could accelerate to. An invisible monster at the center of a trillion suns. Every galaxy has one. Most of Andromeda is invisible. This is not a poetic statement. It is a literal, observational, cosmological fact. The stars of Andromeda, those trillion blazing suns, represent only a small fraction of the galaxy's total mass. The gas and dust add a little more. But the majority of Andromeda's mass, roughly 80 to 90% of it, is composed of something that does not emit light, does not absorb light, does not interact with light in any directly observable way. We call it dark matter. Not because we understand it. Not because we know what it is. Because it is dark, invisible to every instrument we have built that detects electromagnetic radiation, and because it has mass, evident in its gravitational effects. We know dark matter is there because of what it does. The rotation of galaxies is one of the clearest signatures. When astronomers measure how fast stars and gas clouds orbit around the center of a spiral galaxy, they expect, based on Newton's and Einstein's laws of gravity, to find that stars far from the center orbit more slowly than stars close to the center, just as the outer planets of the solar system orbit the sun more slowly than the inner ones. What they actually find is that the rotation curves of spiral galaxies are flat. Stars far from the center orbit at roughly the same speed as stars close to it. This is only possible if there is a large amount of mass distributed throughout the galaxy's halo, mass that the stars are feeling gravitationally but that we cannot see. The dark matter halo extends far beyond the visible disk, providing the gravitational structure within which the visible galaxy sits like a jewel in an invisible setting. In Andromeda, the dark matter halo is estimated to contain roughly 10 times the mass of all the visible stars and gas combined. The galaxy we see, the trillion blazing suns, the spiral arms, the nucleus, the dust lanes, is the fraction of Andromeda that happens to interact with electromagnetic radiation. Gravity alone reveals the rest. What is dark matter made of? We don't know. This is one of the most important open questions in all of physics. The leading candidates have included various hypothetical particles, WIMPs, weakly interacting massive particles, axions, sterile neutrinos, but despite decades of experiments designed to detect them, none has been conclusively identified. Dark matter is the majority of all matter in the universe. It is the scaffolding on which galaxies and galaxy clusters and the large-scale structure of the cosmos are built. It is everywhere, including in the halo of Andromeda, including in the halo of the Milky Way, including in the region of space between the two galaxies. And we don't know what it is. Andromeda is mostly something we cannot see, touching something we don't understand. In this, it is a perfect symbol for the universe itself, the tiny fraction of it that our instruments can detect, surrounded by the enormity of what they cannot. Andromeda does not travel alone. Around it, in orbits that take billions of years to complete, circle a family of smaller galaxies, satellite galaxies, bound by gravity to their enormous parent, each with its own history and character and population of stars. The most prominent are M32 and M110. M32 is one of the smallest and most compact galaxies known. A compact elliptical galaxy about 2,490 light-years in diameter. For comparison, the Large Magellanic Cloud, a satellite of the Milky Way, is about 14,000 light-years across. It is visible to the naked eye under dark skies, a tiny companion star of Andromeda. But M32's small size is deceiving. Its central density, the concentration of stars at its core, is among the highest of any galaxy. Pack that many stars into that small a space, and you get something remarkable. The stellar density at M32's core is roughly 1,000,000 times higher than in the solar neighborhood of the Milky Way. Standing on a planet in M32's core, hypothetically, the radiation environment would be lethal, the night sky would blaze with stars, the nearest of them only light months away rather than light years. M32 is thought to have once been a much larger galaxy, perhaps originally a full-sized spiral. The tidal forces of Andromeda, combined with possible past passages through the larger galaxy's disk, have stripped away its outer stars, leaving only the dense, compact core. M32 is the survivor of a slow galactic disaster. What remains is only the indestructible heart. M110, the other prominent satellite, is a dwarf elliptical galaxy, somewhat larger than M32 but less compact. It contains a modest stellar population and shows evidence of past star formation in its outer regions. Some astronomers believe that M110 may have its own satellite, a tiny dwarf galaxy orbiting a satellite galaxy that is itself orbiting Andromeda. A moon of a moon, in galactic terms. Beyond M32 and M110, the full count of Andromeda's satellites is still growing. Modern wide-field surveys have identified dozens of dwarf satellite galaxies, tiny, diffuse star systems with populations of millions rather than billions of stars, in Andromeda's halo. Many of these are so faint that they were invisible to earlier generations of telescopes. They are detectable only by the statistical excess of resolved stars in certain regions of the sky. The Andromeda dwarfs, as they are collectively called, include some of the most extreme objects in astronomy. Andromeda I, Andromeda II, Andromeda III, and so on through a long list, each a tiny galaxy in its own right, each bound to Andromeda's gravitational embrace. Some of these satellites appear to be old. Their stars formed in the early universe and then star formation stopped, leaving ancient stellar populations that have evolved quietly over more than 10 billion years. Others show evidence of more recent star formation, suggesting interactions with Andromeda or each other have triggered new starbirth episodes. The satellite system of Andromeda is also organized in a way that presents a puzzle. The satellite galaxies don't orbit Andromeda in random directions, as simple cosmological models predict. Instead, many of them appear to be co-rotating in a thin plane, aligned in their orbits in a way that's statistically very unlikely by chance. Similar coplanar arrangements have been found around the Milky Way and other galaxies. Current cosmological theory doesn't fully predict this arrangement. The dwarf satellite problem, why satellite galaxies are arranged the way they are, remains an active area of research. The family of Andromeda is full of puzzles. Andromeda is moving toward us. Not drifting. Not passing by. Moving toward us on a course that, if unchanged, will bring it into a direct collision with the Milky Way. The approach speed is approximately 110 km per second, roughly 250,000 miles per hour. This sounds fast. By human standards, it is incomprehensibly fast. But the distances involved are so enormous that the approach is essentially imperceptible on human timescales. Andromeda has been moving toward us for all of recorded human history. For all of human prehistory. For the entire existence of our species. And it has barely moved at all, relative to the gap that remains. The collision, if it happens as current models predict, will begin in approximately 4 to 4.5 billion years. Let's be precise about what collision means in the context of galaxies. It does not mean what the word implies on human scales. The stars in a galaxy are extraordinarily far apart. The average distance between stars, in the disk of the Milky Way, is several light-years. The probability of two individual stars actually colliding during a galaxy merger is essentially zero. The galaxies will pass through each other, and the stars will follow paths altered by the gravitational chaos of the merger, but individual stars will almost never come close enough to physically collide. What happens to the gas and dust is different. Gas clouds can and do collide, compressing and heating, triggering enormous bursts of star formation. A galaxy merger is accompanied by a starburst. A period of intense, rapid star formation as the gas supplies of both galaxies are compressed and disrupted. What the simulations show is this. In approximately 4 billion years, Andromeda begins to visibly distort the Milky Way. The shape of both galaxies starts to change, their arms pulling toward each other, their disks warping. The first close pass, the two galactic cores swinging past each other at relatively close range, triggers enormous distortions. Both galaxies grow tails of stars, long streamers pulled out by the gravitational forces of the encounter. The sky, for anyone alive on any world in either galaxy, would be transformed, the other galaxy filling the sky with a river of light, millions of new stars blazing to life in the starburst triggered by the collision. The two galaxies swing apart after the first pass. They come back. They interact again. The process of merging, in the simulations, plays out over approximately 2 billion years, with the first pass at around 4 billion years from now, and the final merger completing at roughly 6 billion years from now. At the end of the process, the two spiral galaxies, the Milky Way and Andromeda, both currently beautiful disk galaxies with their spiral arms and star-forming regions, will have merged into a single large elliptical galaxy. The models nickname this future galaxy Milkomeda or Milkdromeda. An elliptical galaxy is fundamentally different in character from a spiral. No disk. No spiral arms. No significant star formation. Just a roughly elliptical cloud of stars, mostly old and red, orbiting the central mass in orbits that have been randomized by the chaos of the merger. A galaxy that has spent its gas, finished its star formation, and is settling into a long, quiet senescence. Milkomeda will be a beautiful object, a vast, softly glowing ellipse of ancient stars. But it will be fundamentally a different kind of thing than either of its progenitors. The Milky Way will cease to exist as an individual galaxy. Andromeda will cease to exist as an individual galaxy. Both will be subsumed into something new. And the Sun. If it still exists, which it will, though it will have left the main sequence and become a red giant by approximately 5 billion years from now, threatening the inner planets with its expanded outer atmosphere, the Sun will be somewhere in the newly formed Milkomeda. Probably flung to a different position than it occupies in our current galaxy, possibly to the outskirts of the merged system. The night sky of Earth, if Earth persists, it may not, the red giant's Sun may engulf it. 6 billion years from now would look nothing like the night sky we see today. The galaxy we see, the Milky Way band, the familiar constellations, will be replaced by something vast and strange. The sky might blaze with the light of the starburst, millions of new stars, created from the compressed gas of the merger. Something we can't see. Can't hear. Can't feel. Something that won't happen for longer than our species has existed, multiplied by 1,000. And yet it is already underway. The approach has begun. 1 trillion stars. Each one a sun. Each one a nuclear furnace, converting hydrogen to helium in its core, releasing energy that travels outward through the stellar interior and eventually leaves as light. Each one with its own temperature, its own color, its own brightness, its own lifespan. Let's spend some time with what those stars are like. A galaxy's stellar population is a record of its history. The oldest stars formed when the universe was young. 10, 11, 12 billion years ago, from the primordial gas clouds of the early universe. The youngest are forming right now, from the galaxy's current gas reserves, in the stellar nurseries of the spiral arms. Andromeda's halo and bulge are dominated by old stars. These ancient stellar populations, sometimes called population 2 stars, contain only small amounts of elements heavier than helium, because those elements hadn't yet been created when these stars formed. The heavy elements. Carbon, oxygen, iron, all the elements that make planets and people, are produced inside stars and released when those stars die. The first generations of stars were made mostly of hydrogen and helium, the original ingredients of the universe. The oldest stars in Andromeda are fossils. They carry in their chemical composition the fingerprint of the young universe. They are as old as anything in existence. The younger stars in Andromeda's disk. The blue-white monsters of the spiral arms, are at the other extreme. They burn fast and hot, fusing hydrogen so rapidly that they exhaust their fuel in millions of years rather than billions. They are the newest chapter of the galaxy's story, recently assembled from gas that has been processed through many previous generations of stars, enriched with the heavy elements that those stars produced and dispersed. Among those stars, stars like our Sun. Andromeda almost certainly contains billions of Sun-like stars, G-type main sequence stars, middle-aged, stable, burning their hydrogen at a leisurely pace that will sustain them for 10 billion years. Each of them a potential parent star. Each of them potentially orbited by planets. Which raises a question we don't know how to answer. How many planets are in Andromeda? We can't directly observe exoplanets in Andromeda. They are far too small and far too faint for any current or foreseeable instrument to detect at 2.537 million light-years. But extrapolating from what we know of our own galaxy, where virtually every star appears to have at least one planet, where rocky planets in the habitable zones of their stars are common, the estimate is staggering. Andromeda likely contains something on the order of 1 trillion planets. How many of them have conditions suitable for life? How many have life? How many have intelligent life? We don't know. We can't know, with current technology. But the numbers involved are so large that it seems improbable, to many astronomers and astrobiologists, that Earth represents the only experiment in life and consciousness in a galaxy of 1 trillion worlds. And that's just Andromeda. Multiply across the hundreds of billions of other galaxies in the observable universe. The numbers become so large that the question of whether we are alone in the universe transforms from a reasonable scientific question into something that feels almost philosophical. Not, is there life elsewhere, but how could there not be? Every galaxy has a biography. Andromeda's is 12 to 13 billion years long, a story that begins in the first billion years of the universe, when the first structures were condensing from the primordial gas of the Big Bang. The early universe, in the moments after the Big Bang, was a nearly uniform sea of hot plasma, hydrogen and helium nuclei mixed with electrons, too hot for atoms to form. As the universe expanded and cooled, atoms formed. And then gravity began its slow, patient work. The tiny density variations seated in the earliest moments of the universe began to amplify, pulling gas together in the slightly denser regions, leaving the slightly less dense regions emptier. Over hundreds of millions of years, the gas clouds grew. They fragmented, collapsed, formed the first stars. The first stars were massive, burning hot and brief, seeding the surrounding gas with the first heavy elements when they exploded as supernovae. The first small galaxies formed, not the grand spirals we see today, but irregular, chaotic little systems, bubbling with star formation, merging and colliding and growing. Andromeda grew through this process. Through accretion, through the merging of smaller systems, through the gradual settling of its gas into the disk that we see today. The stellar streams we discussed earlier are the evidence, dozens of past mergers, their stars now dispersed through the halo, their orbits gradually randomizing over billions of years. The last major merger event that significantly affected Andromeda appears to have occurred approximately 2 to 3 billion years ago. A collision with one or more substantial galaxies that disrupted the disk, created the ring structures we see today, and triggered a burst of star formation. Before that, there is evidence of a complex and violent early history. The stellar populations in Andromeda's halo suggest multiple episodes of accretion and merging in the first several billion years of the galaxy's life. Andromeda was a cannibal, absorbing smaller galaxies, growing larger with each consumption. Our own Milky Way has a similarly violent past. We, too, are built partly from the debris of earlier, smaller galaxies that fell into us and were absorbed. The high-velocity stars in the Milky Way's halo, moving in orbits very different from the disk's rotation, are likely stars from those absorbed galaxies, still traveling in the orbits of their original systems while their original systems no longer exist. We are, both of us, Milky Way and Andromeda. The survivors and inheritors of a long history of galactic violence. In their current state, both galaxies are in a period of relative quiet. Star formation continues but at a lower rate than in their turbulent early histories. The gas supplies have been partly depleted by billions of years of star formation, partly dispersed by the stellar winds and supernova explosions of the stars already formed. The current era is Middle Age, cosmically speaking. And the collision coming in 4 billion years will be the end of that Middle Age, the beginning of the last chapter. In the halo of Andromeda, scattered around the main galaxy like luminous seeds flung by a careless hand, there are approximately 500 globular clusters. Globular clusters are among the oldest objects in the universe. They are roughly spherical collections of stars. Typically hundreds of thousands to several million stars packed into a region only tens to a few hundred light-years across. They orbit the galaxy in the outer halo, following elliptical paths that carry them deep into the galaxy and out again over periods of hundreds of millions of years. The stars in globular clusters are old. Very old. The globular clusters of Andromeda, and of our own Milky Way, were formed in the earliest epochs of the galaxy's history, when the raw material of the universe was first being assembled into stellar systems. Some of the globular clusters in the Milky Way contain stars estimated to be approximately 13 billion years old, nearly as old as the universe itself, which is approximately 13.8 billion years old. Standing inside a globular cluster, if you could, would be extraordinary. Stars would crowd the sky, dense and bright, the nearest neighbors only a fraction of a light-year away. The night sky would be ablaze. There would be no darkness. The combined light of hundreds of thousands of stars would bathe everything in a permanent pale twilight. The globular clusters are the elders of the galaxies. Ancient stellar systems that have survived for the full span of cosmic time, orbiting their host galaxies through all the changes and upheavals of galactic history. Among Andromeda's globular clusters is G1, also called Male 2, which is the most luminous globular cluster in the entire local group of galaxies. It is more than twice as luminous as Omega Centauri, the most luminous globular cluster in our own Milky Way. G1 is so large and massive that it has been proposed to be not a globular cluster at all, but the stripped nucleus of a dwarf galaxy that Andromeda absorbed billions of years ago. The indestructible core left behind when the larger structure was torn apart by tidal forces, just like M32. A ghost of a galaxy inside another galaxy. The globular clusters are also valuable tools for understanding galactic history. Their chemical compositions, the relative abundances of different elements in their stars, record the conditions of the gas from which they formed. By studying the globular clusters of Andromeda and comparing them to those of the Milky Way, astronomers can trace the different evolutionary histories of the two galaxies. The clusters are the archive. Old stars, telling the story of a young universe. Let's follow the light. A star in the outer disk of Andromeda, a yellow star, like our Sun, somewhere in one of the spiral arms, is producing light. Nuclear fusion in its core is converting hydrogen to helium, releasing energy that percolates outward through the stellar layers for tens of thousands of years before finally emerging at the surface as photons. Each photon is a quantum of electromagnetic energy, traveling outward from the star at the speed of light, 299,792 kilometers per second. The photon leaves the star. It travels through the disk of Andromeda, past other stars, past gas clouds, through the warm dust lanes. It exits the disk and enters the intergalactic medium, the nearly empty space between galaxies. Here, there is essentially nothing. The density of the intergalactic medium is approximately 1 atom per cubic meter. A near-perfect vacuum. A silence so complete that even sound, if sound could travel in a vacuum, would have nothing to move through. The photon travels 2.5 million light-years. 2.5 million years of uninterrupted travel through essentially nothing. The world changes around it. On Earth, the human lineage is splitting from the lineage leading to other hominins. 2.5 million years pass. Civilizations rise and fall and rise again. The ice ages come and go. The continents shift, imperceptibly. Species arise, flourish, and go extinct. The night sky slowly changes as the stars drift in their orbits. The photon does not notice. It travels at a constant speed through the unchanging intergalactic void. It has no way of knowing that on a small planet near a medium star, something has arisen that can receive it and wonder about where it came from. It enters the outer halo of the Milky Way. It passes through the disk. It enters the solar system, passing the orbit of Neptune, of Uranus, of Saturn, of Jupiter, of the asteroid belt, of Mars. It arrives at Earth. It passes through the atmosphere, scattering slightly in the air, but mostly surviving. It passes through the lens of a pair of human eyes. It strikes the photoreceptor cells of a human retina. An electrochemical signal travels down the optic nerve to the visual cortex. A faint smudge of light is perceived. You are looking at Andromeda. The photon has completed a 2.537 million-year journey to arrive at the specific arrangement of cells and consciousness that is you, on this specific night, in this specific year. Think about that for a moment. The light you receive from Andromeda is not the light of Andromeda as it exists now. It is the light of Andromeda as it existed 2.537 million years ago. We can never see Andromeda as it is now. The now of Andromeda is unknowable to us, separated from us not just by distance but by the fundamental structure of spacetime, which links space and time in a way that makes simultaneity at a distance a meaningless concept. We see Andromeda's past. We cannot see its present. Looking at the sky is looking back in time. And the further away something is, the further back in time we see it. The most distant objects visible to the most powerful modern telescopes are galaxies seen as they were when the universe was less than 1 billion years old, 12 to 13 billion years ago. We see them as infant galaxies, recently assembled from the first gas clouds, blazing with the intense star formation of galactic youth. We cannot see those galaxies as they are now. They may not exist in their current form, they may have merged, may have evolved beyond recognition. The universe we observe is a museum of light from different pasts, all arriving simultaneously, painting a picture of what was rather than what is. We are time travelers who can only go in one direction, into the past, by looking further away. The story of Andromeda is also the story of the people who spent their lives trying to understand it. We've met al-Sufi, the Persian astronomer who first recorded it. We've met Henrietta Leavitt, who gave us the tools to measure its distance. We've met Edwin Hubble, who used those tools to place it outside our galaxy. Let us meet a few more. Vera Rubin. Vera Rubin was a 20th-century American astronomer who spent much of her career studying the rotation of galaxies, measuring how fast stars and gas at different distances from galactic centers are moving. When she applied this analysis to Andromeda in the early 1970s, building on the work of earlier astronomers, particularly Kent Ford, her longtime collaborator, the results were deeply puzzling. The rotation curve of Andromeda was flat. Stars far from the center were moving as fast as stars near the center, when the theory predicted they should be moving much more slowly. The same was true of every spiral galaxy she and Ford examined. Rubin and Ford were not the first to notice this. Fritz Zwicky had inferred something similar from the dynamics of galaxy clusters in the 1930s, but their work was systematic, thorough, and ultimately undeniable. The rotation curves of galaxies required the existence of dark matter. Vera Rubin spent decades explaining this finding to a scientific community that was initially reluctant to accept it. She was patient, persistent, and rigorous. She was never awarded the Nobel Prize, though many in the field believed she deserved it. She died in 2016 at the age of 88. Her work gave us our understanding of dark matter as a ubiquitous component of galaxies. Her measurement of Andromeda's rotation curve was one of the key pieces of evidence that established dark matter as an observational reality rather than a theoretical speculation. We owe her an enormous debt. Then there is Isaac Roberts, a Victorian-era amateur astronomer who, in 1888, took the first long-exposure photograph of Andromeda and revealed, for the first time, its spiral structure. Before Roberts, Andromeda was known to be a luminous nebula, but its shape was understood only vaguely from visual observations through telescopes. Roberts' photograph showed clearly, unmistakably, the spiral form, the bright central core surrounded by curving arms of fainter stars and nebulosity. Roberts' photograph appeared in scientific journals in 1889 and caused immediate excitement. It was the first visual evidence that Andromeda had the structure that the island universe theorists had predicted for distant galaxies. It didn't resolve the debate, but it sharpened it. If Andromeda was a gas cloud within our galaxy, what process could produce such a beautiful spiral structure? The photograph still carries its power, even now. That dark Victorian-era photograph. Technically primitive by modern standards, showing only the brightest parts of the galaxy, somehow captures something real. Something that looks like a galaxy. Because it is. And finally, Rosemary Wise and Gerard Gilmore, and the many astronomers who have used modern wide-field surveys to map the stellar populations of Andromeda's halo in detail, tracing the stellar streams, identifying the dwarf satellites, reconstructing the merger history. Their work has transformed Andromeda from a beautiful smudge in the sky to a fully mapped, three-dimensionally understood galaxy with a known history and a predicted future. These are the people who spent careers at the eyepiece, or at the computing terminal, or writing software to reduce and analyze the enormous datasets of modern astronomy. They were motivated not by practical benefit. The knowledge of Andromeda has no immediate application to any human problem. They were motivated by the oldest human impulse: I want to know what that is. What is that? That impulse, which we share with al-Sufi in his Persian observatory 1,000 years ago, which we share with every human being who has looked at the smudge in the northern sky and felt the pull of its mystery, is something worth honoring. The astronomer Neil deGrasse Tyson has spoken and written about what he calls the cosmic perspective, the shift in how you see yourself and the world that comes from genuinely internalizing the scale and age of the universe. The Andromeda galaxy is, perhaps more than any other object accessible to the naked eye, the most direct and visceral path to that perspective. It is the most distant thing most humans will ever see with their unaided eyes. And it is looking back at you. Not literally, of course, a galaxy does not have eyes. But there is something about the mutual gaze, your eyes gathering photons that have traveled 2.537 million years from a trillion stars, that collapses distance in a strange and vertiginous way. You are not merely looking at something far away. You are receiving something that has traveled an incomprehensible distance to reach you specifically, at this specific moment. The philosopher Immanuel Kant wrote about the two things that most filled him with awe: the starry sky above and the moral law within. He was, typically of his era, not thinking in terms of galaxies and light years. But the intuition, that the sky's vastness and the inner life's depth are both sources of something that exceeds the comprehensible, seems right. There is a particular psychological effect that comes from looking at Andromeda and really thinking about what you're seeing. Psychologists have studied the emotion of awe, defined as the experience of encountering something vast and beyond your current frameworks for understanding, and found that it has specific, measurable effects on cognition and behavior. Awe reduces the salience of the self. People who experience awe show less self-focused thought, greater sense of connection to others and to something larger than themselves. They make more accurate estimates of time, because awe expands the sense of the present moment. They are more likely to say they have ample time, despite having the same objective amount as before. They are more generous. Awe is cognitively beneficial. It interrupts the default mode of worry and self-reference and replaces it, temporarily, with a kind of spaciousness. Looking at Andromeda, really looking, with the knowledge of what it is, reliably produces awe in people who allow it to. Not because of anything mystical. Because the facts themselves are extraordinary. 2.5 million light-years. 1 trillion stars. A galaxy falling toward us in slow motion over billions of years. The philosopher-naturalist John Muir wrote, "The clearest way into the universe is through a forest wilderness." He was writing about the forests of the Sierra Nevada. But the principle extends, the clearest way into a sense of proportion. Into an accurate understanding of what we are and how much of everything there is through genuine encounter with something that exceeds us. Andromeda exceeds us. In age, in scale, in complexity, in everything except our capacity to perceive it. It is 1 trillion suns. And you can hold it in your eyes. We said that the collision between the Milky Way and Andromeda begins in approximately 4 billion years. But our Sun and Solar System have their own parallel story, unfolding on a similar timescale. Our Sun is currently about 4.6 billion years old. It is roughly halfway through its main sequence lifetime, the period of stable hydrogen fusion in its core. It has approximately another 5 billion years of stable burning ahead of it. In about 1 billion years, the Sun will be about 10% more luminous than it is today. The increased heat output will push the inner edge of the habitable zone outward, toward the orbit of Earth. In about 1 billion years, average temperatures on Earth may begin to rise enough to trigger a runaway greenhouse effect, the evaporation of the oceans, the escape of water vapor to the upper atmosphere where ultraviolet radiation breaks it apart, and the eventual stripping of Earth's water entirely. Earth as a habitable planet may have approximately 1 billion years remaining. We are more than halfway through the era of Earth's habitability. This is not cause for immediate alarm. A billion years is 1,000 million years, more than 3 times the length of time that complex multicellular life has existed on Earth. What might happen in another billion years is genuinely unimaginable. But it is a boundary. A time horizon. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around the core. The outer layers will expand dramatically, the Sun will become a red giant, growing to perhaps 100 to 200 times its current size, possibly engulfing Mercury, Venus, and potentially Earth. The inner solar system will be consumed by its own star. The outer planets, Jupiter, Saturn, Uranus, Neptune, will likely survive, their orbits shifted by the changed mass of the expanded and then dying Sun, but physically intact. And then the Sun will shed its outer layers as a planetary nebula. A beautiful shell of glowing gas expanding into space, leaving behind a white dwarf, a dense, Earth-sized remnant of the stellar core, no longer fusing, slowly cooling over billions of years. This is the death of the Sun. Not a violent death, not the supernova that more massive stars experience. A gentle dying, a slow exhalation. It will coincide, roughly, with the era of the Milky Way Andromeda collision. In the billions of years following the Sun's red giant phase and the merger of the two galaxies, the solar system, in whatever form it takes, will be orbiting in the newly formed Milkomeda. The white dwarf Sun, cooled to invisibility, its planets rearranged by the gravitational chaos of the galactic merger, drifting through the old stellar halo of the merged galaxy. The story of our solar system ends, in this vision, in the quiet darkness of a cooling cinder orbiting through a galaxy born from a collision. But by then, by the time the Sun becomes a white dwarf, by the time Milkomeda has settled into its elliptical shape, whatever intelligence exists in the universe will be so different from anything we can now imagine that to call them our descendants stretches the word beyond recognition. 10 billion years is long. What might a civilization do with 10 billion years? We genuinely don't know. The question floats there, unanswered. Like a smudge of light in the northern sky. Andromeda and the Milky Way do not exist in isolation. They are the two dominant members of a structure called the local group, the cluster of galaxies that constitute our immediate cosmic neighborhood. The local group contains approximately 54 known galaxies, spread over a region roughly 10 million light-years in diameter. Most of its members are dwarf galaxies, small, irregular, or elliptical systems with populations of millions to a few billion stars. The two largest are Andromeda and the Milky Way, which together dominate the group gravitationally. The third largest member, the Triangulum galaxy, M33, is a beautiful face-on spiral about 2.73 million light-years away, close in distance to Andromeda and possibly a satellite of it. M33 is smaller than the Milky Way, about 60,000 light-years in diameter, but visible to the naked eye under exceptionally dark skies. The Milky Way's retinue includes the Large Magellanic Cloud, LMC, and Small Magellanic Cloud, SMC, the two closest satellite galaxies, visible to the naked eye from the southern hemisphere as detached patches of the Milky Way. The LMC, at about 163,000 light-years away, is the site of some of the most dramatic current astronomy. It contains an extremely active star-forming region called the Tarantula Nebula, 30 Doradus, which is producing stars at a rate that dwarfs anything in the Milky Way. And in 1987, a star in the LMC exploded as supernova 1987A, the closest supernova to Earth in 4 centuries, visible to the naked eye, providing astronomers with an unprecedented close-up view of a stellar death. The local group itself sits at the edge of a much larger structure, the Virgo supercluster, an enormous collection of galaxy groups and clusters centered on the Virgo cluster, about 65 million light-years away. This supercluster, which spans approximately 100 million light-years, contains something like 100 galaxy groups including our own. But even the Virgo supercluster is a small component of what modern galaxy surveys have revealed as the true large-scale structure of the universe. A cosmic web of filaments and sheets of galaxies, surrounding enormous voids of nearly empty space, extending in all directions to the edge of the observable universe. The local group is a cluster of galaxies on a filament of this web, a neighborhood in a city, in a country, in a continent, on a planet. And the observable universe, the sphere of space from which light has had time to reach us in the 13.8 billion years since the Big Bang, contains an estimated 2 trillion galaxies. 2 trillion galaxies. Each containing hundreds of billions of stars. Each star potentially orbited by planets. Andromeda, in this context, is our next-door neighbor. The most intimate of all the vast structures out there, the one whose light has been falling on Earth for as long as Earth has existed, the one we can see with our bare eyes, the one that is falling toward us in the slow embrace of gravity. Our neighbor. Everything we know about Andromeda has been learned through instruments. Through the progressive development, over 3.5 centuries of modern astronomy, of better and better ways of gathering light and extracting information from it. The naked eye gave us the smudge. Patient, dark-adapted, careful human eyes have been gathering Andromeda's light for millennia. The telescope. From Marius's first magnified view in 1612 through the great reflectors of Herschel and Lord Rosse, through the Hooker telescope that Hubble used, through the modern giants of professional astronomy, gave us structure. Resolution. The ability to identify individual bright stars, to measure the spiral form, to find the Cepheid variables that revealed the distance. Photography, the ability to record light on a sensitive surface and accumulate it over hours of exposure. Extended the reach of the telescope enormously. The human eye can only see what arrives in an instant. A photographic plate accumulates every photon over a night of exposure, building up a record of faint structures invisible to direct vision. Isaac Roberts' 1888 photograph of Andromeda's spiral form was possible only because photography could record what the eye could not. The spectrograph, the instrument that spreads light into its constituent wavelengths, producing the spectrum, gave us the chemistry and motion of stars. Each element produces characteristic absorption or emission lines in a spectrum, like a fingerprint. By analyzing the spectrum of Andromeda's stars and gas, astronomers can determine their chemical composition, their temperature, and, through the Doppler shift of their spectral lines, their velocity toward or away from us. It was spectroscopic measurement of Andromeda's approach velocity that first told us it was moving toward us. Radio telescopes, receivers sensitive to radio waves rather than visible light, revealed the neutral hydrogen gas in Andromeda's disk, invisible at optical wavelengths but bright in the 21 cm radio emission of hydrogen. Radio mapping gave us the true extent of Andromeda's gas disk, which extends beyond the optically visible disk. Infrared telescopes, operating at wavelengths longer than visible light, between visible and radio, can see through the dust lanes that obscure parts of Andromeda at visible wavelengths. Infrared images reveal the warm dust in Andromeda's disk, the ring structures, the star-forming regions hidden behind the dust. Ultraviolet telescopes, operating at wavelengths shorter than visible light, see the hot, young stars that are the brightest UV sources, revealing the star-forming regions in Andromeda's spiral arms. X-ray telescopes, detecting the high-energy X-rays emitted by very hot gas, neutron stars, black holes, have mapped Andromeda's X-ray binary population, pairs of stars where one member is a neutron star or black hole accreting material from its companion, and provided evidence for the supermassive black hole at its center. The Hubble Space Telescope, orbiting above the atmosphere, which blurs ground-based telescopes, resolved individual stars in the outer regions of Andromeda at optical wavelengths, providing the best current estimates of its distance and stellar population. The Gaia satellite, currently mapping the positions and motions of stars in our own galaxy with extraordinary precision, has also measured the proper motion of Andromeda, its motion across the sky, rather than toward or away from us, helping to refine our predictions of the collision trajectory. And the James Webb Space Telescope, the current pinnacle of infrared space astronomy, is providing new views of Andromeda and other nearby galaxies at sensitivity and resolution never previously achieved. Every generation's best telescopes have revealed something new about Andromeda. And every revelation has been a revelation about ourselves, about the universe we are part of, the history we are embedded in, the future we are approaching. The constellation Andromeda, within which the galaxy sits, is named for one of the most vivid characters in Greek mythology. Andromeda was the beautiful daughter of King Cepheus and Queen Cassiopeia of Ethiopia, the Greek mythological Ethiopia, which was a semi-legendary land at the edge of the known world. Her mother, Cassiopeia, committed the fatal error of boasting that her daughter was more beautiful than the Nereids, the sea nymphs who served Poseidon. Poseidon, enraged, sent the sea monster Cetus to ravage the coast of Ethiopia. The oracle declared that the kingdom could only be saved by sacrificing Andromeda, chaining her to a coastal rock as an offering to the monster. And so she was chained. And so the monster came. But Perseus, the hero who had just slain the Gorgon Medusa and carried her severed head, was flying home over the coast on his winged sandals. He saw Andromeda chained to the rock, the monster approaching. He killed the monster, some versions say by using Medusa's gaze to turn it to stone. He freed Andromeda. He married her. The entire family is commemorated in the northern sky, Andromeda, Cassiopeia, Cepheus, Perseus, and Cetus, all as named constellations, arranged roughly in the mythological geography of the story. Pegasus, the winged horse that Perseus sometimes flies, nearby. The galaxy that we call the Andromeda Galaxy sits within the constellation of Andromeda. The princess chained to her rock, waiting to be freed. There is something poetic about this, if you let yourself feel it. The galaxy, which has been falling toward us for billions of years, which will eventually collide with and merge into our own galaxy, which is in that sense, coming to us, just as Perseus came to Andromeda, named for a princess whose rescue became one of the ancient world's great stories. Not that the myth was aware of the galaxy, of course. But meaning doesn't require intention. The resonance is there for those who want to find it. In modern science fiction, Andromeda has been a frequent setting. Its distance makes it the perfect destination for stories that need to go beyond the Milky Way. Isaac Asimov set part of his science fiction in the Andromeda Nebula. Various Star Trek stories have featured it. The novel, Andromeda Strain, by Michael Crichton, while not about the galaxy per se, borrowed its name for something alien and threatening. The galaxy has entered popular culture as a symbol of the distant, the alien, the unreachably far. Carl Sagan, in his television series Cosmos, used Andromeda as a touchstone for the cosmic perspective, the shift in awareness that comes from genuinely grasping the scale of the universe. He stood in front of images of the Andromeda Galaxy and talked about what it meant to be on a pale blue dot in a nondescript corner of one galaxy, looking out at another. The physicist and author Richard Feynman, when asked what he thought was the most beautiful thing he knew about the universe, reportedly talked about the way that physics, the equations, the understanding, had given him a deeper appreciation of a moonlit night or a starry sky than he could have had without it. The knowledge didn't reduce the beauty. It added dimensions to it. Looking at Andromeda and knowing what you're seeing, knowing the distance, the scale, the trillion stars, the dark matter halo, the falling trajectory, the eventual merger, doesn't diminish the faint smudge in the sky. It transfigures it. That smudge becomes one of the most extraordinary things in the observable universe. The light from Andromeda that reaches your eye on a dark night was produced by approximately 1 trillion individual stars. Your eye is simultaneously receiving photons from 1 trillion separate sources, each one a nuclear furnace, each one a sun. The distance from Earth to Andromeda is 2.537 million light-years, or approximately 24 quintillion kilometers, that is 24 followed by 18 zeros. If you could drive to Andromeda at highway speeds, the journey would take approximately 250 billion years, more than 18 times the current age of the universe. Andromeda is approaching the Milky Way at approximately 110 kilometers per second. At this rate, it closes the distance by about 9.5 million kilometers every day. This sounds significant until you realize the total distance of roughly 2.4 million light-years. It would take approximately 75 billion years to cover that distance at this speed alone. The actual collision timeline of 4 billion years reflects the accelerating effect of gravitational attraction as the two galaxies close. The Andromeda galaxy contains an estimated 500 globular clusters, nearly twice as many as the Milky Way's approximately 150 to 200. Some of these globular clusters may themselves be the stripped nuclei of ancient dwarf galaxies that Andromeda absorbed billions of years ago. The supermassive black hole at Andromeda's center has a mass of approximately 100 to 140 million solar masses, between 25 and 35 times more massive than the Milky Way's central black hole, Sagittarius A*.